Okay, hi everybody. So this is my promised solution for that dreaded normal line problem. And let me tell you, this one was a toughie. And really the toughest part was the algebra. So let's go through this. So the first thing I did here, as you can see, is that I went ahead and made a drawing. And let me hang on a second. Let me pause you for 1 second. Okay, and I made this drawing here that I made in class, just so I have a clear sense of what's going on, okay? And at the end of the day, for part A, we have to show that this distance between the y-int of the normal line and where that normal line intersects the curve again, that is a constant value of d, it's some constant, okay? So again, this visual is nice. So just walk with me here. And I'm also going to ask you how nice and clear this video is. My goal is to become a viral YouTube star. So the point of tangency, I use the notation x naught comma y naught. That's the point of tangency right here. Now the naught subscript, that is to make sure that we very clearly distinguish between x naught, y naught standing in the place of an actual value versus like the variable x, right? The variable x in this function, y equals px squared, this variable x is changing. So I'm using the not notation to denote a specific value of x. Now, in this case, since I have this curve, I know that y naught is just px naught squared, right? Because this point has an x coordinate of x naught, and then of course a y coordinate of, plug in x naught into y equals px naught squared. Here is my point of tangency. Slope of the tangent line in general is 2px. And here's that clarity again. The slope of the tangent line at that point of tangency then would be 2px naught. See that distinction? Okay. This is the general derivative. This here is the derivative evaluated at that specific point x naught. So the slope of the normal line at the point of tangency is going to be the opposite reciprocal because perpendicular lines have that opposite reciprocal slope relationship. All right. So then I'm down to the equation of the normal line, and here's that point slope form that we talked about. Right, Julia? So I just dropped in the slope right here, and look what I did. I dropped in the coordinates of that point of tangency. All right. And now what I'm going to need to do, if I look back at my drawing, I have to at some point get an expression for the y-int of that normal line, an expression for this point here, you know, where this line, the normal line, intersects the curve. But let's deal with the y-int of the normal line. Now we're back in the world of Algebra 1 or Math 1 even. So, and here's where it's going to be really important. Look at this equation here. Remember all that subscript conversation? So make note of the difference between x, the variable, and x naught standing in place of a specific value of x, okay? And how do you find the y-int of a line? Well, the y-int of a line, the y-int of any curve, really, you just plug in 0 for x. So when I plug in 0 for x, I get this. Right? And of course, when you want to find the y-int, you want to eventually solve it for y. If you follow my work here, so the y-int is right here. And if you want to write it as an ordered pair, that is the y-intercept. All right, that's the y-intercept. Now, okay, so we got an expression, okay, we got the ordered pair of this point. We now need to find the y coordinate of this point, right? Because this distance d is going to be the y coordinate of that point minus the y coordinate of that point. Specifically, we're talking about only vertical distance, okay? So we have to find, everyone, the coordinates of that point of intersection, point of intersection, point of intersection. What does that make you think of when you think of where two curves intersect? It makes you think of a system, okay? And what two curves are we looking at? Well, we're looking at the parabola and we're looking at the normal line, all right? I will say this, everyone, if you've gotten this far to kind of at least framing the question, from here on out, it is just an algebraic vomitous mess. And I'm going to say this on the record. You will never have a question on an assessment that involves the algebraic mess you're about to experience, okay? I always give this question first, the first of the year, because it's a forced review of a whole lot. But on a quiz or a test, you will never, ever, ever have questions that are just ridiculously messy algebraically. Are you ready? Now, I'm wondering, how do we solve a system? Maybe you use substitution, maybe you use linear combination. Oh, we can't use linear combination or elimination because these aren't both lines, right? So the best I can do is a substitution. I'm going to substitute in y for y. What happens? Boom, right there. Okay, now this is where you have to really, keep your x and x naught straight. Our goal here is to solve for x, the variable x. So I did a little cleaning. I just multiplied both sides of the equation here by 2p x naught. Okay, now if you look at this equation, we're solving for x. And you know what kind of equation that is? This equation right here, it's in disguise. It's a very ugly disguise, but it's nothing other than just a straight up quadratic equation. And what I did from here to here is I just kind of isolated, A, B, and C, if you will, right? Because this is the coefficient of the x squared term. -1 is the coefficient of the x term. This is all constant. Now, if you jammed this into the quadratic formula, I think what you get is a world of pain. So what I did here is I factored, and I factored in a really devious way. So here's what I did. Look what I did, and you're going to probably express a couple of things, and if it's not PG, maybe express it to your neighbor. But so look at this. Now you're wondering, Miss Yam, how did you factor that? Well, guess what, everyone? Look at this drawing. Oh my gosh, look at this drawing. This normal line, it intersects the parabola twice, obviously. The here and here. Oh my goodness. You want to know something, everyone? It just occurred to me. I think I made this question more difficult than it had to be. It asks you, it didn't want you to pick the point where it intersected it again. It just wanted you to use the point of tangency. No wonder. Oh, well, let me just pause and clean that up. Oh, silly. Well, you know what the heck? Let's just do the hard one, the hard version. That just occurred. Well, oh, I'm such an idiot. Anyway, the reason why I knew it factors this way is because I know that x naught has to be one of the factors because this point right here is x naught comma px naught squared. Well, if you know this has to be one of the factors, you can just kind of do some backwards logic and figure out the other quadratic factor, kind of unfoiling, if you will. And then when you set this factor equal to 0, because it has to be set equal to 0, and solve for x, you get this. And then you clean here, okay? So there, this right here is the y coordinate of which point, everyone? Which point, which point, which point? Yes, this point, this point. And I just made this question so much more difficult than it has to be, but you know what? These kinds of moments, they're very good for you. It's kind of like eating broccoli. You don't like it on the way down, but long term, it's good for you. Now, where are we? Okay. Vertical distance between the y-int of the point, the y-intercept, right here, here's the y-int, minus, right here, here's the y-coordinate of the other point. And if you do this correctly, right, and this is where it's just algebra, clean, 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 clean. At the end of the day here, what you get is that vertical distance d, okay? Now, the reason why I have a suspicion that I picked the harder point is because at the end of the day, we really shouldn't have any x naughts around because the question said just find it in terms of the distance should be only in terms of p. So let's go do it together in live time. Oh my gosh. Hopefully I didn't just cut you off here. All I need, ladies and gentlemen, is just maybe 3 days of getting this technology perfect, cleaned up. Let's do the correct point live time together. So really the distance they wanted was, oh, so embarrassing, so embarrassing. They wanted this vertical distance, everyone. Goodness, this is the vertical distance, D here, between the y int and the point of tangency. Oh my gosh, it would be so much easier. Well, so that vertical distance D, okay, is the y coordinate of the y-intercept. Where did that go? It is 1 over 2p plus px naught squared. 1 over 2p plus px naught squared. Now, what's the y-coordinate of this point? Yes, it's just px naught squared, so minus px naught squared. At the end of the day, d just equals 1 over 2p. Oh my gosh, that was so much easier. Oh, is that funny? That is funny. Okay, now part B, what's the range of y-ints of the normal line? Well, let's just play with this visually. The idea is if you look at this normal line here, okay, here's that normal line. And the idea is what's the range? What's the range of those y-intercepts? And so the idea is what's really happening to those y-intercepts, right, as this point gets kind of dragged along the parabola. It seems that as that point of tangency gets closer to 0, right, the normal line gets very close to vertical, okay? So, what's interesting is that as x naught approaches 0, it seems to be that the y int of the normal line seems to approach positive infinity, maybe, right? But then what happens as x naught approaches positive infinity? Well, let's see. So let's go back here. So here's my y-intercept. So the question is, what's happening as x naught, as we drag x naught closer to 0 or drag x naught closer to positive or negative infinity? Well, let's see. Let's set up some limits. So here we go. Well, let's look as x approaches positive infinity. And as x approaches positive infinity, it appears that this limit approaches positive infinity, right? And as x approaches 0, right, we have this is the y-int approaches 1 over 2p. So the range of y-ints is 1 over 2p to positive infinity, and definitely not inclusive, okay, because you never can get to 0, really, because if the tangent line ever was at 0, the y-int would be like every single y value, right? All right. Okay, well, that was quite fun. All right, bye, everybody.